Dear students, in the previous class I have explained the concept behind analysis of variance. In this class, with the help of Python we will solve that problem, because previously in the previous class we have solved it manually. Now we will use the help of Python, we will solve that problem. This was the problem which was given. What is the problem is, there are 3 different teaching methodology. We have to say which teaching methodology is more influencing on the student performance. Okay. In Python, so I have taken A is an array 4, 3, 2, B 2, 4, 6, C 2, 1, 3. If you type stats.f underscore one way, just you call ABC, you run that one, you will get this was our f value, this was our f, that is a calculated f value, this is the p value. Suppose if the alpha equal to 5%, it is more than 5%, so we have to accept null hypothesis. That is what our previous result also. Now we will use that another command that is pandas.melt command. We will see the purpose of this command for doing Anova. pd.melt allows you to unpivot data from a wide format into long format, that is data with each row representing a data point. So for that purpose, import pandas as pd, import numpy is np, import math from scipy, import stats, import scipy, import statsmodel.api as sm, from statsmodels.formula.api import OLS, from matplotlib import pyplot as plt. So first we will load the data. The data I am going to save the data, the given in the Excel file I am going to save in the object called data. So data equal to pd dot read underscore excel one way dot xlsx. So I have loaded. When I run this data, now the data is appearing, say column 1, column 2, column 3. So 0, 1, 2, that is your index. Next what you have to do, for running the data I need to have the data in this format. What is that format is? So TM1, teaching methodology 1, teaching methodology. If a teaching methodology 1, there may be some numbers. In teaching methodology 2, there may be some numbers. In teaching methodology 3, there may be some numbers. So this says your treatment. So the next one says the value. Suppose I want to have the data in this format. For that you have to use the following command, that is data underscore new, I am going to call it is that way. pd.melt data.reset underscore index parenthesis comma id underscore vars equal to in the square bracket index comma value underscore vars in square bracket teaching method 1, teaching method 2, teaching method 3, data underscore new dot column equal to index comma treatment comma value. So this is the syntax for using the melt function. So if you run this data underscore new, we will get this kind of output. You see, previously the data was 0, 1, 2 format. Now what we are saying, all teaching methodology 1, it is grouped in this way. This is group 1, this is your group 2, this is group 3. Now only there was only 2 column, one is treatment, another one is value. Now after getting this data into this format, for converting this purpose the melt command is used. So model equal to OLS, OLS is ordinary least square method, in quote value tilde c treatment comma data equal to data underscore new fit. Then if you write Anova underscore table equal to sm.stats.anova underscore lm model type 1, when you run this you will get the Anova table. This represents degrees of freedom for treatment, because there was a 3 column, treatment is 2, residual is 6, because for column 1 there are 3 elements, so 3 minus 1 2 degrees of freedom. Similarly for column 2 also another 2 degrees of freedom, for column 3 also another 2 degrees of freedom, totally 6 degrees of freedom. So sum of square is 6, here sum of square is 12. So mean sum of square is 6 divided by 2, that is 6, this is 12 divided by 6, that is 2. So f value is 3 divided by 2, this was the p value. This also we got it previously with the help of When we do it manually, we compared this 1.5 and we got the same value. This is with the help of Python, we are also getting the same result. Now I will go to the formal definition of ANOVA in a conceptual overview. Analysis of variance can be used to test the equality of 3 or more population means. Data obtained from observational or experimental studies can be used for this analysis. We want to use the sample result to test the following hypothesis. In ANOVA, what is the hypothesis? H naught equal to mu1 equal to mu2 equal to mu3, it may be n number of columns. Alternative hypothesis is not all population means are equal. H naught equal to mu1 equal to mu2 equal to mu3. HA is not all population means are equal. If H naught is rejected, we cannot conclude that all population means are equal. So when you reject it, that means there are some unequal population means. So rejecting H naught means that at least 2 population means have different values. What are the assumption for analysis of variance? For each population, the response dependent variable is normally distributed. In our previous example, the performance of the student is the dependent variable, the independent variable is teaching methodology. The variance of the response variable denoted by sigma square is the same for all populations. Why this assumption is required? When you are comparing more than 2 groups, the basic assumption is that the variance of that group should be same. This concept we have explained when we are conducting 2 sample test, and the observation must be independent. Look at this normal distribution. This is the sampling distribution of x bar given null hypothesis is true. Sample means are close together because there is only one sampling distribution when H naught is true. Look at this normal distribution. There are 3 normal distribution. Here the sampling distribution of x bar given H naught is false. What is H naught is false? What is H naught here? H naught equal to mu1 equal to mu2 equal to mu3. If it is a false, what will happen? It will not be from same population, it will be from different population. So the sample means come from different sampling distribution and are not as close together when H naught is false. In analysis of variance, we can classify, one is one way ANOVA, another one is two way ANOVA. There is one more thing in between, that is called RBD, randomized block design. We will see when we will go for randomized block design. In one way ANOVA, we are going to do the F test. F test will help you to decide whether the null hypothesis should be accepted or rejected. When you reject a null hypothesis, then Tukey-Kramer test will help you which 2 pairs are equal or which 2 pairs are not equal. Then this side is a two way ANOVA, then we will go for interaction effects, that we will see in coming classes. In this class, we will see how to do the F test, how to do the Tukey-Kramer test. What is the general ANOVA setting? Investigator controls one or more factors of interest. In our previous example, the teaching methodology is the factor. So each factor contains 2 or more level. In our case, you see, suppose if the pressure is the one parameter, maybe high or low, that is level. So high is one level, low is another level. Level can be numerical or categorical. Here the example is it is a categorical. It need not be categorical, it may be a continuous variable also. So different levels produce different groups. Think of the groups as population. We can say each groups can be, we can consider as the population. Observe effect on the dependent variable. So what we are going to do in ANOVA is, what is the effect of this treatment on the dependent variable. Next we will see experimental design, the plan used to collect the data. Only the experimental design, we will have a plan to collect the data and we will see the effect of this data on the how this treatment is influencing the data. The first one method called completely randomized design. In our previous example, the students are allocated to 3 groups randomly. That is an example of your completely randomized design. There is no bias, because what will happen there, suppose if you consider the student IQ level, then you are allocating that student into different category of classes then that is not called biased method. So, what is happening here, the experimental units are assigned randomly to the different levels. So, subjects are assumed homogeneous, only one factor or one independent variable, that is why it is called one way ANOVA, because here teaching methodology is the independent variable, the student performance, that is the marks, is the dependent variable. There also we can have 2 or more levels. If you are analyzing one factor analysis of variance, it is called one way ANOVA. If there are 2 independent variable, that is a 2-way ANOVA. So, what we are doing, the basic concept behind is, we are finding the variance due to between the treatment and variance within the treatment. So, that will go to your numerator, that is nothing but your SS treatment. That is why I wrote SSB. When you divide by degrees of freedom, this is MSB divided by SSE divided by degrees of freedom, that is variance within the treatment, this is nothing but your MSE. So, we will find variance between the treatment, then variance within the treatment, then we will go for F test, then I will explain what is this ANOVA table. So, what is a null hypothesis? For a CRD completely randomized design, mu1 equal to mu2, mu3 equal to mu k, not all population means are equal. Here assume that a simple random sample of Nj has been selected from each of the k populations or treatment. There are k treatment. In our previous example, there was a 3 treatment, 3 factors. 3 factors means 3 levels. For the resulting sample data, let Xij value of observation, I for treatment j, Nj is number of observation for treatment j, Xj is sample mean for treatment j, Sj square sample variance for treatment j, Sj is the sample standard deviation for treatment j. First we will find out between treatment estimation of population variance sigma square. The estimate of sigma square based on the variation of the sample mean is called mean square due to treatment, it is denoted by MSTR. In our example previously we have used, we can have MSB, that is mean square due to between columns. So, how we are finding this MSTR is nothing but Nj number of elements in column j, Xj that column j mean minus the overall mean whole square divided by k minus 1. K is the number of columns, here 3 minus 1. So, the denominator is the degrees of freedom associated with sum of square treatment. The numerator is called the sum of square due to treatment, SSTR divided by degrees of freedom. Between treatment estimation of population variance sigma square, the mean square due to treatment, that formula which you have seen previous slides. So, what is the meaning of the k? K is the number of groups, k number of columns, Nj is the sample size from group j, Xj bar is the sample mean from group j, X double bar is the grand mean of all data values, overall mean. Next we will see within treatment estimate of population variance. The estimate of sigma square based on the variation of the sample observations within each sample, this is more important term, within each sample is called mean squared error, is denoted by MSE. So, mean square error, how we are doing that one? Nj in column j, how many element is there? Minus 1, that is our degrees of freedom, Sj square. Actually how it has come, you see, if you want to know Sj square, what is the formula? Sigma of x minus, for example, xj whole square divided by n minus 1. So, this instead of writing numerator, that can be written as Sj square into n minus 1, that is why it is written Nj minus 1 Sj square divided by Nt is denominator is the degrees of freedom associated with error sum of square. I will tell you what is the Nt in the next slide. K is the number of groups, Nt is the number of treatment. Here this Nt is nothing but the overall degrees of freedom. From the overall degrees of freedom, if you subtract the degrees of freedom for between the columns, then you will get the degrees of freedom for your SSE, that is error sum of square. In our previous example, you might have seen the NT is 9 minus 1 8 and the K is there was 3 columns. So, it is 2, it was 6 degrees of freedom in our previous problem for MSE. The formula for mean squared error is sigma of j equal to 1 to k nj minus 1 sj square divided by nt minus 1, where nt is total number of observations, where k is number of groups. Comparing the variance estimates, that is F test. If the null hypothesis is true and Anova assumptions are valid, the sampling distribution of MSTR divided by MSE is an F distribution with MSTR degrees of freedom is equal to k minus 1, that is number of column minus 1, and MSE degrees of freedom is NT minus 1. NT is total number of sample minus k is number of groups. If the means of the k populations are not equal, the value of MSTR divided by MSE will be inflated because MSTR overestimates sigma square. So, what is the meaning of this one is, we are finding F. The value of F is MSTR divided by MSE. There are two possibilities. It may be equal 1 or less than 1 or greater than 1. If it is equal to 1, what is the meaning is variance due to treatment is equal to variance due to individual error. If it is greater than 1, the variance due to treatment is more when compared to within the error. When it becomes less than 1, if the MSE, that is error due to individual difference is more when compared to treatment, then it will become less than 1. So, you see this one, if the mean of the k populations are not equal, the value of MSTR by MSE will be inflated because MSTR overestimates sigma square. Hence, we will reject because F value will become very big. When F value is very big, we will reject H naught if the resulting value of MSTR by MSE appears to be too large to have been selected at random from appropriate F distribution. Yeah, this is the situation. So, what will happen when F is bigger number, well, obviously we will be landing on the rejection side, we will reject null hypothesis. When you reject null hypothesis, we will say mu 1, mu 2, mu 3. This was your null hypothesis. Alternative hypothesis is mu 1 not equal to mu 2 not equal to mu 3. So, when you reject null hypothesis, we can conclude that these means are not equal. And one more thing, this is the F distribution, it is not normal distribution, it is a right skewed distribution. Okay. This is the Anova table setup. So, what will be written? Sources of variation. So, there may be variation may be due to treatment, variance due to error. So, sum of square is sum of square treatment, error sum of square. Here the degrees of freedom is k minus 1, here nt minus k. Generally, if you SST degrees of freedom is nt minus 1, nt is total number of element minus 1, when you subtract this nt minus 1 minus k minus 1, that will give you nt minus k. So, MSTR is nothing but we have to divide this SSTR divided by corresponding degrees of freedom. So, it will become mean treatment sum of square. When you divide SSE divided by corresponding degrees of freedom, mean error sum of square. So, the ratio of, you see, MSTR divided by MSE, always in the denominator there should be error term, because when you go for two-way ANOVA, we have to remember that the denominator always there will be error term. Then we can find out corresponding p value. This is what we have done previously when you are explaining my first example. Generally what is happening, this SST divided by its degrees of freedom nt minus 1 is the overall sample variance that would be obtained if we treated the entire set of observation as one data set, right. When you divide this SST by corresponding degrees of freedom, that is overall variance. With the entire data set as one sample, the formula for computing the total sum of square is SST is sigma j equal to 1 to k, sigma I equal to 1 to nj, xij minus x double bar square. So, this total sum of square can be splitted into two parts. One is treatment sum of square, and error sum of square. If this treatment sum of square is dominating, even without going further test, we can say that there is a influence of treatment on the response variable. Anova can be viewed as the process of partitioning the total sum of square and the degrees of freedom into their corresponding sources, that is treatment and error. Dividing the sum of square by the appropriate degrees of freedom provides the variance estimates and the f value used to test the hypothesis of equal population means. Okay, what is the hypothesis? The null hypothesis as usual, mu1 equal to mu2 equal to mu3. Alternate hypothesis is not all population means are equal. The test statistics is the ratio of mean treatment sum of square divided by mean error sum of square. The p value approach as usual for hypothesis testing also, if the p value is less than or equal to alpha, we have to reject null hypothesis. If you are using critical value, the f value is greater than your value which you got from the table, that also we have to reject our null hypothesis. In this class what we have seen, we have taken one problem, that problem we have solved with help of Python. Then I have explained the theoretical background behind this Anova. Then I have explained what is the total sum of square, then what is the treatment sum of square, then error sum of square, then what is the degrees of corresponding degrees of freedom. The next class we will take extension of this class is, once we reject a null hypothesis, we have to say which two means are equal or not equal. So, that analysis is post hoc analysis. We will continue in the next lecture with the new topic of post hoc analysis in Anova. Thank you very much.